Hello, I'm Dr. Dupre, and in this section we're going to discuss the cross product of two vectors in space. Now, the cross product is more complicated than the dot product geometrically because it actually involves the full 3 dimensions of space. In fact, it's only in 3 dimensions that we can make a cross product. And in order to deal with it, it's best to keep the geometry firmly in mind. In fact, in many applications in physics and engineering, it's the geometry of the cross product when you're dealing with cross products that will be the crucial thing that will help you through. So let's look at the geometry of the cross product of vectors. So here in this picture, I've drawn 2 vectors. Here's vector V, vector W, and they're just vectors somewhere in space. In other words, don't think of V and W as being in the plane of the blackboard. They're vectors in space, and they have some angle between them. I've drawn them with their tails together, and the angle that V and W make is theta. Now what I've done is drawn a parallelogram with these edges V and W and denoted its area by capital A. In order to form the cross product of V and W, what we do is we form a vector whose length is the area of that parallelogram, but whose direction is perpendicular to the plane of V and W. For instance, V is like my thumb and W is like my index finger, and they're like this. You see what they're doing is making a plane like that. And so the direction of V cross W is perpendicular to that plane. And the way we get the direction is by what's called the right-hand rule. That is, when I make my hand turn from V towards W, then my thumb points in the direction of the cross product. So in this case, you see with W sort of pointing back into the blackboard somewhat, then V cross W as my hand turns from V towards W in the plane of V and W makes my thumb go in this direction. So V cross W is this vector which is perpendicular to the plane of V and W, and so therefore, in particular, it's perpendicular to each of V and W. And not only that, its length is the area of the parallelogram. So in symbols with the double bars, length of V cross W equals capital A, and what that means in terms of the angle, the length of V cross W is length of V, length of W, times the sine of the angle theta. Let's look at this in a little more detail, see geometrically why we have that formula. Notice, if I draw a parallelogram whose one side base has length B and the other side has length C, I can drop a perpendicular from the top side down to the bottom. So here's a right angle. And notice it cuts off a right triangle, and I can shift this triangle over to the other edge of the parallelogram, and that makes a rectangle. And so obviously, if h is the height of the parallelogram, the area is base times height, since it's the same as the area of this rectangle. But on the other hand, notice if this side has length c, the height h is c times sine theta. So the area, being base times height, is b times c sine theta. And so that's where our formula for the length of the cross product comes from. The length of the 2 vectors, the length of v would be b here. In other words, if I make that v, and if I make this one w, so length w equals c, then what I'm getting for the length of v cross w is the area A, which is length V, length W, sine theta. Well, for instance, for practice, let's compute the cross products of the basic unit vectors along the axes. Notice they're at right angles to each other. And what's the sine of 90 degrees, or pi over 2? Sine of pi over 2 is 1. So this factor is 1 in each case. Now these vectors, these basic unit vectors along the axis having length 1, this is 1. So the length of each of these cross products is 1. So that means when I take I cross j, It's a vector which is perpendicular to the xy plane, and it has unit length. That means it's either k or negative k. Which is it? Well, my hand pointing out of the board in the direction of positive x, curl my fingers towards the y-axis, j, my thumb points up, and so in fact we get k. I cross j is k. How about j cross k? Well, in this case then, put your hand in the direction of j, curl your fingers towards k, and notice your thumb points out of the blackboard, so j cross k is I. What about k cross I? Well, in this case, put your fingers in the z direction, curl your fingers out of the blackboard, twisting me up pretty good, but we can do it and see that my thumb points in the direction of j. And notice what this means. When I look at this first equation, I cross j equals k, and notice they're just in alphabetical order, I, j, k, easy to remember. When I start permuting these symbols, in other words, move this one back to this position, this one back to this position, and then this one moves out, comes around front, j cross k equals I. Do it to this one. Move this one here, this one here, this one moves out, comes around front, we get k cross I equals j. We call this cyclic permutation of the symbols, and it makes it very easy to remember how the basic unit vectors form their cross products. What about what's going to happen if I reverse the order? Well, that reverses the sense. For instance, if I'm forming v cross w in this picture, it points out of the blackboard. What happens when I form w cross v? It goes into the blackboard. So changing the order in a cross product is going to reverse the direction, but of course it can't change the area of the parallelogram, so the length stays the same. So consequently, what we have is a very simple formula for reversing the order. V cross w is the negative of w cross v. Very important to remember when it comes to cross products. Now, the cross product, in fact, obeys all the usual distributive and scalar laws that, like the dot product does. And so when I take the component form of vectors and write them in terms of I, j, k using these basic relations, I get a kind of a complicated formula for getting the cross product of vectors. And that's easy to express in terms of determinants. So in order to do this, if I want to form v cross w, what I've done here is I've written v and w one under the other, and here they're components. And one way to think of this is we're forming a 3 by 3 determinant by putting the basic unit vectors up here on top. But what we're doing is what's called expanding by minors. In other words, to get the I component, we eliminate this column and the row that the vectors are in, and that would tell us to concentrate on this little square here, and that gives us what's called a little 2 by 2 determinant. And to compute that, we multiply down the diagonal a2 times b3, and then subtract, multiplying down this diagonal, a3 b2. So multiply this way, and then subtract what you get multiplying by this. To get the second component, cover up the middle column, and notice we have the two outer ones, and we form a little 2 by 2. And in the middle one, we have a negative sign. And then for the final component, cover up the last one. You see we have the little 2 by 2 determinant, A1, A2, B1, B2. So in order to demonstrate this, it's actually easy. For instance, suppose we have v equals negative 3, 2, 5, and w is 2, negative 1, 3. In order to maybe help at first, you can put the unit vectors there and draw the vertical lines. To remember, you're computing a determinant, in effect. V cross w is. And so what are we going to get for the first component? Simply cover up the first column and look at 2 times 3 is 6 minus 5 times negative 1. 6 minus negative 5 is 6 plus 5, which is 11. How about the second component? Cover up the middle column. Now we have negative 3 times 3 is negative 9, minus 2 times 5, that's negative 10, and negative 9 is negative 19. But remember, for the middle component, we change the sign when we're through computing, so we would get plus 19. And now finally, for the last component, cover up the last column. Negative 3 times negative 1 is plus 3. Minus 2 times 2 is 4. So that's 3 minus 4 is negative 1. And so there we've computed the cross product of two vectors using components. It's easy to do with a little practice. In other words, when you just write the one vector on top of the other in terms of its components, putting the first factor on top, then you simply look at these component expressions. To get the first one, cover up that first column, look at that little 2 by 2. To get the second one, cover up the center one and look at the 2 by 2, and then don't forget to change the sign. And then for the final component, cover up the last component, and then you can see the little 2 by 2 determinant. You can just write it down. With a little practice, you can do it just like that. One of the useful facts to remember about the cross product is that the length of the cross product of two vectors is the area of the parallelogram formed with those two vectors as edges. Now that can be used in problems for area. Find the area of any parallelogram having vertices P with coordinates 2, 1, 3, Q with coordinates negative 1, 0, 2, and R with coordinates 1, negative 2, 1. Notice there are only 3 points, and of course a parallelogram has 4 vertices. Well, let's look at a little schematic picture here, because in fact what I claim is that it won't matter how we complete these 3 points to form a parallelogram. Notice here's a triangle with points P, Q, and R schematically. I could come out here with a line parallel to this edge, completing a parallelogram like that, or I could come over in this direction and form a parallelogram, or I could come down here and form a parallelogram. Notice those are the only 3 parallelograms that will have these 3 vertices. How do their areas compare? Let's look at the 2 top parallelograms, the one which has base, the edge from P to R. So here's one of them coming over leaning to the left, and here's the other kind of leaning to the right. Since they both have the same base length, and notice they both have the same height, therefore they have the same area. Let's look at the parallelogram on the left, leaning left, together with the one down underneath. Notice they have a common base, which I can think of as the edge from Q to R here, and then they have the same height, this distance from point P to the edge QR, and consequently both these 2 parallelograms have the same area. In other words, the area of all 3 of those parallelograms is exactly the same. It will not matter which point I choose as a 4th point to create a parallelogram. Another thing to notice is that if I wanted the area of the triangle formed with these 3 points, that's half of the area of the parallelogram. So what I'm doing, which results in finding the area of the parallelogram, could be equally well applied to find the area of the triangle. In the end, we just divide the result by 2. So in order to begin this, remember, for instance, if I'm looking at this parallelogram here, its area is the length of this vector cross this vector. So I'm forming the vector with tail at Q and tip at P, and the vector with tail at Q and tip at R. And so we simply need to calculate those 2 vectors and form their cross product. So coming over here, The point P has coordinates 2, 1, 3. The point Q has coordinates -1, 0, 2. And so notice then the vector with tail at Q, tip at P, is equal to angle bracket 2, 1, 3 minus angle bracket -1, 0, 2. That is, notice this is the vector with tail at the origin and tip at P. This is the vector with tail at origin and tip at Q, and so it's the difference of those two vectors which gives us the vector QP. Now, you might notice that when I form that subtraction, we're going to get 2 minus -1 is 3, 1 minus 0 is 1, 3 minus 2 is 1. I could quickly have looked how I wrote these one over the other. I wrote the tail point underneath the tip point. And so they're looking in vertical columns. 2 minus -1 is 3. 1 minus 0 is 1. 3 minus 2 is 1. So you can notice that that's a quick way to get vector components for vectors from one point to another. Simply put the tip point on top, the tail point underneath, and subtract in corresponding columns. Well, let's do the same thing and get the vector whose tail is at Q and whose tip is at R. So I've written the point R with its coordinates on top and the point Q again with its coordinates underneath, and so now we just subtract in columns. 1 minus -1 is 2, -2 minus 0 is still -2, and 1 minus 2 is -1. So there's the components for the vector QR. Now, let's bring over QP. Remember, it's 3, 1, 1, and we need to form the cross product then of these two, QR cross QP. Now, remember the way to do that, the simplest way is with the determinate method, and just to help you remember, I'll put on top of that the IJK, and remember we think of this as doing a little determinant, which is 3 by 3 expanding by minors of using the top row. So the I component is this little 2 by 2 determinant over here to the right. That is, for the first component, cover up the first column and look at the little 2 by 2 array of numbers and make the determinant. -2 times 1 is -2, minus the product of these two, minus, well, the product of -1 with 1 is -1, comma. Now for the second component, remember we have to change the sign of the determinant. We cover up that middle column. 2 times 1 is 2, minus -1 times 3 is a -3, but for that determinant we have to change the sign of the result. And then finally for the last component, we cover up the last column. We'll have 2 times 1 is 2, minus -2 times 3 is -6. So we have 2 minus -6, and of course then -2 plus 1 is -1. 2 minus -3 is 5, then change the sign, becomes -5, and 2 minus a -6 is 8. So there we have the cross product calculated. Its components are -1, -5, -8. And so to get the area we're interested in for the parallelogram, we just take the length of that cross product, which of course is the square root of the sums of the squares of its components. -1 squared is 1, -5 squared is 25, 8 squared is 64. So we have 26 and 64, which is 90. Now, the square root of 90 is approximately 9.4868, but in any case, the square root of 90 is the area of the parallelogram that we're looking at for those 3 points. Any parallelogram formed with those 3 points as vertices has area square root 90. That means that any triangle, or the triangle, of course, with those 3 points as vertices, has area 1/2 the square root of 90. One of the most often used applications of the cross product of vectors is to the computation of torque in physics and engineering and in mechanics. For instance, if I have an object here and I'm going to turn it about an axis, for instance, suppose my finger here is the turning axis, by applying a force like this, by definition the torque is the cross product of the displacement vector from the turning axis to the point where the force is applied. So if I'm applying a force here, the displacement I want to consider is the vector whose tail is right here at this point and whose tip is at the point of application. So maybe I'll use the little pen to be the vector for displacement. And so I apply a force this way, then the cross product of the pen displacement with my index finger indicating the force, that cross product is the torque. So let's calculate a torque. So in the problem I want to deal with, a pipe wrench 2 feet long is used to turn a large pipe fitting by exerting a 50-pound force perpendicular to the pipe and making a 60-degree angle at the end of the wrench handle. Calculate the applied torque. Now remember, we're dealing with a pipe fitting, so the pipe itself will be the axis. And so the wrench is fitting onto that pipe, and we're applying a force at the end to turn it, you see. So let's look at a picture of this. I've drawn it up here kind of crudely. So here we're looking down the pipe fitting. The pipe itself is the axis of rotation coming out of the board. And here's a big pipe wrench, 2 feet long. And of course, I want the axis of rotation to be here, and 2 feet away is the point where the force is applied. And of course, in our problem, the magnitude of this force is 50 pounds, and it's perpendicular to the axis. And so consequently, here's the pipe fitting is the axis of rotation, and so the force is making an angle like that. And so consequently, you can see in this picture that's going to turn the pipe fitting. Now, by definition then, the torque, capital T, is a vector which is given as R cross F, where R is the displacement vector from the axis of rotation out here to the point where the force is applied, and so I've moved it down here to make it easier to see. So here's the displacement vector R from the axis to the point where the force is applied. Now the force is making a 60-degree angle here, and so we want to calculate the torque as R cross F. And notice, to calculate the cross product of R with F, we can get the direction using our right-hand rule. So remember, I'm going to take the R and shift it over. Imagine it's shifted over so their tails are together. The R is pointing out this way. And so we would be rotating like that. And so you see my thumb is coming out of the blackboard. Boom. So we know the direction of the torque vector is this way. This is sometimes called the right-hand screw rule. You can think of this, if this were a kind of a giant screw, turning it this way would be loosening it, whereas if I turned the wrench around and pulled this way, I'd be tightening into the board. Like when you turn a faucet, to clamp it down, you turn this way, and to open it up, you turn that way. It's the right-hand rule. Okay, so our direction for our torque is toward us out of the blackboard, and so now the question is, what's its magnitude? Well, remember, the magnitude of the torque then is simply the magnitude of the cross product, which is length of R, length of force, times the sine of the angle between the two. Well, when I move the displacement vector out here, here's the angle, which is 120 degrees. And notice the sine of 120 degrees is the same as the sine of 60 degrees. Here's a 60-degree angle. Here's a 120-degree angle. The y-coordinates are the same there. And so consequently, what we have is length of R, length of F, times the sine of 60 degrees. Now our displacement vector is 2 feet long, So we put a 2 for the length of r. Our force magnitude is 50 pounds. And what's the sine of 60 degrees? Well, let's draw a little triangle. This is a 60, 30 degree right triangle. And we know that we can think of this as having sides 1/2 here, 1 here, square root of 3 over 2 there. So the sine of 60 degrees is simply square root of 3 over 2. So consequently, the 2's cancel, and what we get for our torque is simply 50 times the square root of 3. And the units here are, well, our displacements in feet, our forces in pounds. So this is 50 square root of 3 foot-pounds. And so there we have the calculation of our torque in this simple problem. Notice you may have run into torque before, and if you haven't, in, for instance, auto mechanics, there are many of situations where torques have to be tightly controlled in order to keep from tightening nuts and bolts too tightly, but in order to also make sure that they're tight enough. So torque is an important concept. Well, now that you've seen how we work with the cross products, you've seen examples in computing areas of parallelograms. You could also use it to compute areas of triangles. Remember, the area of a triangle is just half the area of the parallelogram you would make with the 3 vertices. And so consequently, it has many geometrical applications, and as well, it applies to computations of torque.